On page 107, we have rules for drawing line bond or Lewis structures of compounds. We've had most of this before, but there's an important thing we want to add right here. Let's recap. Rule number 1 says the least electronegative atom is central. We've seen that before. For example, in carbon dioxide, carbon has a lower electronegativity and is central. Rule number 2 is that group 1A atoms are never central. Hydrogen, lithium, sodium, potassium only ever form one bond at maximum, so they must be terminal, like this. They can't be central. And this is a new rule, but extremely important. In oxyacids, what's an oxyacid? Well, it's an acid that's made of oxygen and hydrogen, hence the word oxyacid, and a nonmetal. So for example, nitrous acid, carbonic acid, hypochlorous acid, etc. That's an oxyacid. So the rule is in oxyacids, acidic hydrogens are bonded to oxygen, and the oxygens are bonded to the central atom. So you get that. It's really important. Acidic hydrogens. If the hydrogens are acidic, they're bonded to oxygens, and all the oxygens are bonded to the central atom. So for example, we write the formula. Hypochlorous acid is HClO, but that's not its structure, is it? We know it's an acid. It has an acidic hydrogen, so where is the acidic hydrogen bonded to? All acidic hydrogens are bonded to oxygens, and oxygens bonded to the central atom. So HOCl is the proper structure or layout of hypochlorous acid. And sometimes you'll see it written that way as formulas, HOCl, without the bonds. But this is definitely incorrect. Not so. Rule number 4, we draw and arrange Lewis symbols of the atoms so they are centered around the central atom. We've done that already. Note that, or recall that, non-bonded electron pairs may remain unbonded. The non-bonded pairs can bond or they may not, but the unpaired single electrons will always form bonds. And then we join covalently bonded atoms with line bonds. But for ionic bonds, we don't draw line bonds, we transfer electrons and we show charges. I have an example here for how you'd apply this to drawing the structure of carbonic acid, which is an oxyacid. And I won't spend a lot of time here, but basically you lay out the Lewis symbols of the atoms following the rules that we just stated. Notice that all of the acidic hydrogens are bonded to oxygen, and carbonic acid, H2CO3, is a diprotic acid, meaning that both of its hydrogens are acidic. So we see that acidic hydrogens are bonded to oxygen, and all the oxygens are bonded to the central atom. Once you lay this out, you can't go wrong. They're all covalent bonds, and you come up with the structure of carbonic acid. Alright, so get a pencil and paper, please, and let's put this all to work. We're going to look at the reaction of carbonic acid, a diprotic acid, with 1 mole of sodium hydroxide. And that will produce water and 1 mole of sodium bicarbonate. So even though carbonic acid is diprotic, we're just going to neutralize one of its acidic hydrogens in this first reaction, forming 1 mole of water and left with sodium bicarbonate. So what we've already learned is that a hydrogen ion donor is a Bronsted acid. That would be carbonic acid. And a hydrogen ion acceptor would be a Bronsted base. That would be hydroxide ion. Sodium ion will just be a spectator ion. We also learned that in an acid-base reaction, when an acid donates a hydrogen ion or loses a hydrogen ion, then it forms a conjugate base. So bicarbonate ion is the conjugate base of carbonic acid because it has 1 less proton. At the same time, sodium hydroxide accepts a hydrogen ion or proton and it forms its conjugate acid, which is water. Right, so if you are given the pKa of the acid or the pKb of the base, you could then calculate the pK values of the conjugate pairs. So in the first example, you'd have to be given the value of pKa. You can't calculate it. It's usually measured in solution, and we'll do that in the lab. You'll see how it's done. In any case, let's say you're given the pKa of carbonic acid at 6.4. What would be the pKb of its conjugate base, sodium bicarbonate? We can calculate that. Remember that pKa plus pKb for any conjugate acid-base pair equals 14. So the conjugate base pKb is 14 minus the pKa of its conjugate acid. In this case, that's 14 minus 6.4 is 7.6. That's the pKb of sodium bicarbonate. 6.4 and 7.6 are conjugate acid-base pairs. They add to be 14. Okay, so hydroxide is a strong base. Its pKb is negative 1.74. What's the pKa of its conjugate acid? Well, it'll simply be pKa is equal to 14 minus the pKb, which is a negative 1.74. So the pKa of water is plus 15.74. That's a very weak acid. So the Bronsted-Lowry theory of acids and bases is very useful. It helps us identify conjugate acid-base pairs. But it's only part of the story. Let's talk about the Lewis acid-base theory. It helps us understand mechanisms. So let's draw the Lewis structures of carbonic acid. I'm going to do it kind of quickly to save time because we've done many examples. We have hydrogen singly bonded to oxygen. Recall that all the acidic hydrogens are bonded to oxygens, and all of the oxygens are bonded to the central nonmetal. So H2CO3 looks like this with one more oxygen, and the one oxygen is doubly bonded to the central atom. Now each oxygen is in group 6A, so it has to have 6 electrons that it owns to be neutral. So right now, this oxygen now owns 6 electrons, right? It has 8 in the valence shell because it owns 4 and shares another 4. But if we count what it owns half of what it shares. So this is a neutral oxygen atom. The same would be true for this one. And what about the oxygen up here? Again, 2 non-bonded pairs of electrons. This oxygen up top also owns 6 electrons. 1, 2, 3, 4, and 1, 2, half of what it shares. The formal charge of all the oxygens are 0. The formal charge of carbon is 0. It owns 4 electrons, half of what it shares. The formal charge of hydrogen is also 0. Let's draw the Lewis structure of sodium hydroxide. And we've drawn lithium hydroxide already, so this should be easy for you to write out. Remember, the bond between the sodium and the oxygen is not covalent, it's ionic. All right, so let's think about the Lewis acid-base mechanism. So recall that a Lewis acid is defined as being an electron pair acceptor. A Lewis base is an electron pair donor. The mechanism is the transfer of electrons from the electron donor, the base, to the electron acceptor, the acid. It's the oxygen anion in hydroxide that is the electron donor. Any one of these 3 non-bonded pairs are equivalent. Any one of them will donate a pair of electrons to one of the 2 hydrogens in carbonic acid. And that's the formation of the oxygen to hydrogen bond in water. Recall that hydrogen is monovalent. It can't have a bond with the oxygen at the same time have another bond with this other oxygen. In order to form the bond with hydroxide, it has to leave behind the pair of electrons it's currently sharing with the oxygen in carbonic acid. That is the mechanism of the reaction. It shows the transfer of electrons from electron donor to electron acceptor. Now we can now draw the products. Let's draw the Lewis structures. When hydroxide bonds to this hydrogen ion, it's a hydrogen ion because it leaves electrons behind, it forms a water molecule. Like so. Now let's keep track of the electrons. I'll color this pair of electrons green, and this pair now is this shared pair here. Okay, what happens to the carbonic acid? Well, it loses the hydrogen ion, so what's that going to look like? Well, the left side is about the same. No change there. The oxygen on the right instead of having just 2 pairs of non-bonded electrons, it now has 3 pairs and a negative charge. And the sodium ion will hang out somewhere near that in solution. It's ionically associated, it's not covalently bonded. So let's color these. Here I'll use blue. So this shared pair of electrons, this blue here, becomes this unshared pair of electrons here. This is sodium bicarbonate. Notice the charge on this oxygen over here is -1 because it owns 7 electrons instead of 6. Oxygen is in group 6A. When it owns 6 electrons in its Lewis structure, then it's neutral, but if it owns 7, it's -1. Right, so that's the acid-base mechanism. Carbonic acid is diprotic. That is, it has 2 hydrogens that can be removed. So if we added a second molecule or second mole of sodium hydroxide, we could remove this second hydrogen from bicarbonate. All right, so here's the reaction for the sodium bicarbonate reacting with a second mole of sodium hydroxide, losing another hydrogen ion, forming another molecule of water, and forming sodium carbonate. What's the mechanism for that reaction? To see the mechanism, we need to use Lewis structures. So here's the Lewis structure of sodium carbonate, and here's the Lewis structure again of a second molecule of sodium hydroxide. As before, the hydroxide is the base, the electron donor. It donates a pair of electrons to form a bond with the hydrogen ion of the acid. Well, it's going to become an ion here because hydrogen can only have 1 bond. It must leave behind this pair of electrons. And the oxygen, being an electronegative atom, is quite willing to accept the pair of electrons. Let's draw the product for that. So again, hydroxide becomes another molecule of water. Again, let's keep track of those electrons. Here's a pair of electrons that's being shared to form a bond, and here's that pair of electrons now that it is shared. And then I'll color this pair of electrons blue. The shared pair becomes the non-bonded pair. Okay, so here this will be carbonate. The right side is unchanged. That's like so. But the oxygen on the left has more than just 2 non-bonded pairs. It now has 3 non-bonded pairs. And here's another sodium ion hanging out around here. So the blue shared pair of electrons becomes this blue unshared pair of electrons in sodium carbonate. So notice that carbonic acid has 2 acidic hydrogens. It is called a diprotic acid. The strength of the second proton as an acid is referred to as pKa2. And it's going to be different than pKa1. In the case of bicarbonate, its pKa is 10.3. That's quite a bit weaker than pKa1. Recall that these pK values are log values. So that's really 4 powers of 10 or 10,000 times less acidic, right? Higher values are less acidic. Why would it be so much more difficult to remove the second hydrogen ion than the first one? What is it that makes it more difficult? Well, think about it. In the first case, you're taking away a hydrogen ion from a neutral acid. In the second case, you're taking a hydrogen ion from something that's already negative. It's going to be even more difficult to separate it. And that's pretty much true for all the polyprotic acids, that the pKa2 is typically a higher value, meaning less acidic, usually by about 3 pK values, usually by at least 1,000 times less acidic. In this case, it's 10,000 times less acidic, or 4 pK values. Now we saw that the pKb of sodium bicarbonate was 7.6. There's no way we could use these 2 values, 6.4 and 7.6, to calculate 10.3, the pKa. They're unrelated. We'd have to measure pKa1 and we'd have to measure pKa2, and we'll be doing that in the lab, and I'll show you how that's done. But once we know pKa2, we could easily calculate pKb for this base. pKb of carbonate is equal to 14 minus the pKa of the acid it came from. That would be 14 minus pKa2. 14 minus 10.3 is 3.7. So that's considerably stronger base than bicarbonate with a pKb of 7.6. So let me write this down. We had carbonic acid. It's pKa of 6.4, that's a weak acid. pKb, it doesn't have one. It can't accept any more protons. It is not basic in any sense. When carbonic acid deprotonates, it forms bicarbonate. We calculated the pKb of bicarbonate to be 14 minus 6.4 or 7.6. We looked in a book and found some author had determined its pKa is 10.3. When that weak acid loses a hydrogen ion, it forms carbonate minus 2. And so we could calculate the pKb of carbonate. 14 minus 10.3 is 3.7. There is no pKa for carbonate. It has no more protons to give. It's not in any way acidic. So we have these values that, so these add to be 14 and these add to be 14. I want to introduce another concept to you here, and we'll reinforce all of these things I've been explaining in multiple examples, but I'd like to get them all out in front of us now. Bond lengths between atoms can be measured, and these are the bond lengths of the carbon to oxygen bonds in carbonic acid. Notice the carbon to oxygen single bond is 140 picometers long. Both of these carbon to oxygen single bonds are the same, but notice the carbon to oxygen double bond is shorter. It's only 120 picometers. Now, why would that be? Why would a double bond be shorter than a single bond? It's generally always the case. Does it make sense that since there are two pairs of electrons being shared between the nuclei, there's more attraction, there's a stronger overall force of attraction, and the bond will be tighter? It's a good rationale. It works. What's interesting is after carbonic acid loses the proton, it forms bicarbonate. And now look at the bond lengths. The carbon to oxygen single bond on the left is still 140 picometers, but strangely, both the carbon to oxygen single bond on the right and the carbon to oxygen double bond have changed. They're both the same length. They're both 130 picometers, somewhere between 140 and 120. What's going on? Well, it turns out that this negative charge on the oxygen is actually going to be shared between the two oxygens, the doubly bonded oxygen and this anionic oxygen. So the true structure would look something like this. Negative charge is shared by both the oxygen atoms, and so we draw a dotted line indicating that there's like a partial bond here, and so we have, like, you could say 1.5 bonds on the top and 1.5 bonds on the bottom. Now this is a more realistic vision of what's actually present in the structure of the bicarbonate ion, but this particular better model is actually quite useless. We can't do much with it other than say this is what probably it is. So instead we choose to keep these inexact models of bicarbonate ion, and we perform a process which we call resonance. Let's draw the structure of the bicarbonate ion. So this is one possibility. The negative charge is on the rightmost oxygen. But there's another possibility. It could be on the upper oxygen. So we join resonance structures by two-way arrows. And let's draw the other case where the negative charge is on the upper oxygen and the oxygen on the right is now the double bonded oxygen. we enclose all possible resonance structures in square braces to identify them as being resonant structures. All right, so take a look at these two. Notice what we've done is we said the negative charge can be on either oxygen, and we can envision this as flipping back and forth, thousands of times a second if you want, such that the model together looks like this blurred, more realistic model. But these resonance structures are far more useful, as you'll see. So how do we show the interconversion of one resonance structure to the other? Because we're saying, in a sense, in our model, that they flip back and forth. There are 3 rules for resonance. I'm going to ask you to write them down with me, and then I'll show you them in the notes. But it's useful for you to write them down. 3 rules for resonance. Rule number 1 is that an atom, I'll just call it X, with a non-bonded pair of electrons can do this. We say that non-bonded pair of electrons can become a pi bond as long as it stays attached to the same atom. As long as it stays attached to the same atom. As long as it stays attached to the same atom. I'm saying this on purpose, so to keep that, don't forget that. Now, there is a change in charge that occurs. The atom on the left owns how many electrons? It owns 4, and I've drawn it as being neutral. So in the structure on the right, it only owns 3. So if it lost an electron, it's no longer owning 4, it has to be positively charged. There's a second rule for resonance, and let's start with an atom that has a pi bond on it. We can say that the pi bond can become a non-bonded pair of electrons on the same atom, provided it's attached to the same atom. And that would look like this. So it's pretty much the reverse of the first rule. We start with a pi bond, it can become a non-bonded pair of electrons on the same atom. Now again, there'll be a charge change. I've drawn this atom as being neutral and owning 3 electrons. Now it owns how many electrons? 4. So what's the charge? It has to be minus. So when these changes occur, there has to be a change in charge. Just count the electrons. And the third rule is the simplest of all. We say that an atom that has a double bond and a single bond, well, that pi bond in the double bond can just flip over and become a pi bond on the other side of the atom as long as it's connected to the same atom. You hear me? It has to be connected to the same atom. So now we'd have this structure on the right. And there's no charge change here because in both cases that atom owns 3 electrons. So these rules for resonance, again, they're just hypothetical bookkeeping rules, but they really help us to explain and draw mechanisms in reactions, as you'll see, particularly in organic chemistry. Let's apply these 3 rules to these resonance structures. Which of these occur where in the process? So in order for this first resonance structure to become the second resonance structure, what happens to the oxygen on the right? Notice it goes from an atom with 3 pairs of electrons attached by a single bond to become 2 pairs of electrons attached by a double bond. Isn't it occur like this? Any one of these 3 non-bonded pairs of electrons becomes a pi bond on the same atom, right? That was rule number 1. And notice the charge change. It went from being negative to being neutral. So it lost 1 negative charge. Now when this happens, the other bond has to break. The pi bond has to break because otherwise carbon would have 5 bonds and it can't. So the second step would be for this oxygen on the top to go from a neutral doubly bonded oxygen to a negative singly charged oxygen. So what happens to bring about this change? Wouldn't that be rule number 2? Notice a pi bond flips up, becomes a non-bonded pair of electrons. So here, at the same time as rule number 1 is occurring, rule number 2 is occurring. And that'll give us a second structure. And you could apply, although we don't do this, we could apply the same rule returning. You could say, okay, then rule number 1 could occur here, and then rule number 2 could occur here, and these electron transfers would allow these structures to flip back and forth thousands of times a second, if you will, and we get this mixed structure. These are called resonance structures. We join them by two-way arrows. We put them in closed braces, and we draw the arrows to show the transfer or movement of electrons. Typically, we don't show the arrows on the last one. You can if you want, but it's not required. All right, let's go a little further with this. Let's consider the carbonate ion. Carbonate is CO3 negative 2, and we would draw it with two oxygens with negative charges, but there's a third oxygen with a pi bond that could be involved in resonance. And in fact, the true structure of carbonate has the negative charge spread over all three of these oxygens, and the bond lengths are not what you would predict if you just thought of this as being a single bond and a double bond. It's more like it's a mixture. Let's draw all the possible resonance structures of carbonate ion, and then we'll show the electron transfers that would allow that to occur. Two-way arrow. Just draw it again. Let's this time put the double bond on the right carbon. It doesn't really matter what order you put them in. We can always figure out a way to do it. So double bond on the right and single bond on top. Now let's go to the last structure. We'll put the double bond this time on the left. So we'll have O double bond C and then two singles. Those are all three possible resonance structures. Right. Let's put some electrons in. The doubly bonded oxygen is neutral. It's got two pairs of electrons. The singly bonded oxygens, they have 6 unpaired electrons and a negative charge. Notice this is carbonate, CO3 minus 2. Doubly bonded oxygen is neutral. The singly bonded oxygens in carbonate are negatively charged, so they have 3 non-bonded pairs of electrons. Notice this is CO3 minus 2 carbonate. Right, so what are the rules for resonance we could apply here? Okay, so take a look at our rules. Rule number 1, you don't have to memorize the rule numbers, just learn how to do it. So in order to go from the first structure to the second structure, what have we done? Well, notice that this singly bonded oxygen with 3 non-bonded pairs becomes a doubly bonded oxygen, and a pair of electrons is not there, and the charge has been reduced by 1. So any one of these 3 non-bonded pairs of electrons becomes a pi bond. That changes the charge, reduces it by 1, and gives us that structure. At the same time as that is happening, the carbon-dioxygen double bond becomes a carbon-dioxygen single bond with an extra pair of electrons. How would that happen? The pi bond moves up here. That's rule number 1, and this is rule number 2. Okay, how about going from the second structure to the third structure? What's happening here? Okay, so the oxygen on the left goes from being a single bond with 6 unpaired electrons with only 4 unpaired electrons. So how about if we take any one of these 3 pairs of electrons, form the pi bond, and then this oxygen on the right, this electron pair has to move up here. That's a rule number 1. Again, rule number 2. We don't draw arrows for the third. We understand it can reverse. So those are the 3 possible resonance structures of carbonate ion. This probably looks a little strange. It's okay. It's going to take some practice. It usually does. But with some practice, follow the same thinking, it gets easier. And I'll do some with you as we go along. So those are rules for resonance. Resonance structures are joined by 2-way arrows. They're put in square braces to identify them. We draw arrows. I'm coloring them red here, curved arrows to show the movement of electrons, to show the interchange of these structures. On page 113, we have the rules for resonance listed here. Let's get some more practice. Let's draw the neutralization reaction of phosphoric acid with sodium hydroxide. It's a triprotic acid. It'll give us lots to work with, and we can draw resonance structures along the way, calculate pKa's and pKb's. We can talk about conjugate acid-base pairs as well. So get yourself a pencil and paper and buckle up. Let's look at the neutralization of phosphoric acid one step at a time with sodium hydroxide. So the first neutralization would produce monosodium dihydrogen phosphate and water. Let's draw the Lewis structures of the molecules and show the mechanism for it. So phosphoric acid is an oxyacid. It's triprotic. All three hydrogens are acidic. pKa1 is listed as 2.1. pKa2, which we'll get to in a little bit, is listed as 7.2. That's 5 powers of 10 less acidic, more difficult to remove the second proton, and pKa3 is 12.3, almost another 5 powers of 10 weaker again still. So quite a difference. How do we draw phosphoric acid? Like any oxyacid, we draw all acidic hydrogens bonded to oxygens and all the oxygens bonded to the central atom. All three of the protons in phosphoric acid are acidic. Phosphorus is a group 5A element, so I know it's going to have 5 electrons. It's bonded to 3 oxygens, so one here. The oxygens are bonded to a hydrogen because they're acidic hydrogens. And we need a third oxygen. I'm just going to bend it because I want to save some space here, that's all. Then we have another oxygen, a fourth oxygen, which is going to be bonded directly to phosphorus. It will need a double bond. So draw in the number of electrons you think every atom should have. Right? By this time I'm thinking you're recognizing that oxygen is a group 6A. It likes to have 2 bonds. Whether they're single or double, it likes to have 2 bonds and 2 non-bonded pairs. So let's go ahead and give them that. Let's count up the number of electrons that we should have in our structure. Hydrogen is in group 1A. There's 3 of those. Phosphorus in group 5. Oxygen in group 6A. There's 4 of those. 24 and 8 is 32 valence electrons. So we should see 32 valence electrons in our structure. 32 valence electrons, so that agrees. So at this point, since we've drawn so many Lewis structures, you don't really need to draw the Lewis symbols. You can simply write down the atoms with the number of bonds they normally have and the number of non-bonded pairs they would have to be neutral. So for example, oxygen is in group 6A. To be neutral, it should own 6 electrons, 2 bonds and 2 non-bonded pairs. And this has a formal charge of 0 and it has a full octet. That is true for all 3 of these oxygens. The doubly bonded oxygen, likewise, 2 bonds and 2 non-bonded pairs. It's got 8 electrons in the valence shell. It owns 6. It's neutral. Hydrogens are neutral. What about phosphorus? Group 5A. It should own 5 electrons. 1, 2, 3, 4, 5. Half of what it shares. So it's neutral. What about the fact that it has more than 8 electrons in the valence shell? It has 5 bonds. Is that a concern? No, because phosphorus is a third period element and they can be hypervalent. So that's the structure of phosphoric acid. Next we'll draw sodium hydroxide, which is our base. We've drawn this a few times now, so you should be able to quickly write it down. Alright, so hydroxide is our Lewis base, electron pair donor. It's going to donate a pair of electrons to one of the hydrogens in the acid. And hydrogen can't have 2 bonds at the same time, so it must lose the pair of electrons that it currently is sharing with the oxygen in phosphoric acid. And what will we form? We're going to form water again, HOH. And we'll get monosodium dihydrogen phosphate. What would be the pKb of monosodium dihydrogen phosphate? It would be 14 minus the pKa of phosphoric acid. 14 minus 2.1, 11.9. Okay, so what about dihydrogen phosphate? It is also weakly acidic. Let's draw its structure. Let's react it with a second mole of sodium hydroxide. Same mechanism. The base donates a pair of electrons to one of the acidic hydrogens. The hydrogen ion leaves, leaving its pair of electrons behind. We're going to form another molecule of water. Now we'll have disodium monohydrogen phosphate. Now we said earlier that the pKa of monosodium dihydrogen phosphate is 7.2, and that's from the literature. So what's the pKb of disodium monohydrogen phosphate? The pKb is 14 minus 7.2, which is 6.8. Now, monohydrogen phosphate is still acidic. It's pretty weak. It's 12.3 pKa, but let's write the equation for its neutralization. All right, so same mechanism. The base is the electron pair donor to one of the hydrogen ions. There's only one left. And we'll produce, this would be trisodium phosphate. Remember, the sodium-oxygen bond is ionic, so the sodium ions will be floating around in solution. All right, so if the pKa of monosodium phosphate is 12.3, that's pKa3, is 12.3. What's the pKb of trisodium phosphate? Well, 14 minus 12.3 is 1.7, which is a moderately strong base. So the way these are numbered, notice we have pKa1 for phosphoric acid, pKa2 for dihydrogen phosphate, pKa3 for monohydrogen phosphate. This base, trisodium phosphate, is referred to as pKb1, and then pKb2 is the value of monohydrogen phosphate, and then pKb3 is the value for dihydrogen phosphate. Let's summarize this. So here I've listed phosphoric acid, dihydrogen phosphate -1, monohydrogen phosphate -2, phosphate -3. The pKa of phosphoric acid is 2.1, and the pKb of its conjugate base, 14 minus 2.1, is 11.9. The hydrogen phosphate, its pKa, is 7.2. The pKb of its conjugate base, monohydrogen phosphate, is 6.8. These add to be 14. The pKa of monohydrogen phosphate is 12.3, and the pKb of its conjugate base is 1.7. They add to be 14. Phosphoric acid can only be an acid. It can't be a base. It can't accept any more protons. Phosphate is only a base. It can't be an acid. It has no more protons to give. Let's get some practice drawing the resonance structures of phosphate ion. Square braces. Draw the structure of phosphate. Here we have 3 oxygens with a negative charge, and one of them is neutral with a pi bond. So this neutral oxygen with the pi bond can be involved in resonance and share the negative charge with the other 3 oxygens. You could think of each oxygen as sharing an equal amount of charge. Let's draw all 4 structures that are possible, and then we'll put the arrows in. So we'll simply move the double bond around clockwise. It doesn't matter where you put it. I'm just doing it this way so I can keep track of it. Okay, there's one position. Let's move the double bond to the bottom this time. And finally we'll put the double bond on the left. All right, let's put in the non-bonded pairs of electrons. The doubly bonded oxygens are neutral. The singly bonded oxygens, as we saw on the left, they're all negatively charged. They have 3 non-bonded pairs of electrons. They all own 7 electrons. They have a formal charge of -1. Alright, so I think I put all the electrons in correctly. Can we now draw the arrows, the resonance arrows, to show how these would interconvert? So look at the leftmost structure and its neighbor. Okay, so to go from a singly bonded negatively charged oxygen to a pi bond neutral, and that would produce the second structure. To go from the second structure, this pi bond is going to move. Notice it's going to come back out here and become a non-bonded pair of electrons, and then we need a pi bond on the bottom. So let's bring this pair of electrons back out here and bring one of these pairs of electrons in to here. How about going from the third structure to the fourth? This pi bond has to become a non-bonded pair. Let's move it out. And then at the same time, this single bond has to become a double bond. And that's it. There's all the resonance structures of the phosphate ion. Let's take the chlorine oxyacids. Hypochlorous acid, HClO, is a weak acid with a pKa of 7.6. When it loses a hydrogen ion, its conjugate base would be hypochlorite, whose formula would be what? ClO minus. What's the pKb? 14 minus the pKa. 14 minus 7.6 is 6.4. Chloric acid with an extra oxygen is quite a bit more acidic. And this are more than 5 powers of 10 more than 100,000 times more acidic. The conjugate base of chloric acid is called chlorite. It would have the formula ClO2 minus. Its pKb would be 14 minus 2, which would be 12. So it's quite a bit weaker base because the conjugate acid is stronger. We'll talk about this in a little bit. If we add one more oxygen, we get chloric acid, whose pKa is now 3 powers of 10 more acidic still, 1,000 times more acidic. Its conjugate base is chlorate, ClO3 minus, and its pKb will be 14 minus a minus 1 will be plus 15. So a weaker still conjugate base. And perchloric acid is one of the strongest acids. Some books list it as pKa negative 10. Perchlorate ion would be ClO4 minus, and therefore its pKb would be 14 minus a minus 10, or 14 plus 10 is plus 24. That is a really weak conjugate base of a very strong conjugate acid. I'd like us to draw the structures of some of these and consider resonance, and we'll talk about why these differences in acidity apply for removing the same hydrogen ion from different oxyacids. Let's start by you drawing these oxyacids, and then I'll fill in the rest. H is an acidic hydrogen, so it's bonded to oxygen, and all the oxygens are bonded to the other nonmetal. That's the structure of hypochlorous acid. Put in the number of electrons you think it should have. Chlorine's in group 7A, so if it's neutral, it's going to own 7 valence electrons, just like it was if it was HCl. Oxygen in group 6A, it should own 6 electrons. That is the correct structure of hypochlorous acid. If you count the electrons, that's what it should have. Every atom has an octet around it. Every atom owns the number of electrons to make it neutral. So hypochlorous acid reacting with sodium hydroxide, Lewis base donates a pair of electrons to the Lewis acid. Oxygen to hydrogen bond must break. Hydrogen can only have one bond at a time, giving us then the hypochlorite ion, and the hydroxide is protonated to water, and we're left with the sodium ion floating in solution somewhere near the anion. Let's draw next the structure of chlorous acid. It would be HClO2. That's the correct structure for chlorous acid. What's the mechanism? Our base is the electron donor to the acid, forming sodium chlorite and water. Please draw chloric acid, HClO3. Let's finish up that reaction, and we'll draw the mechanism. So when chloric acid reacts with sodium hydroxide, the acidic proton is removed, and the pair of electrons stays behind. It forms sodium chlorate and water. Okay, one more to go. Can you draw the structure of perchloric acid? That's HClO4. That's the correct structure. Let's finish up the neutralization reaction. Alright, so what's the mechanism? Lewis base donates a pair of electrons to form a bond with the acidic hydrogen, the proton of the acid. A pair of electrons stays behind. Wind up with perchlorate ion. Yes, there should be a sodium cation there, and water. So I've listed these 4 oxyacids and their 4 conjugate bases, and I listed their pKa's and their pKb's. Take a look at the acids. Look at the huge increase in acidity as we add more oxygens. From pKa of about +8 to -10, that's approximately 18 powers of 10 difference. That number is too large to even comprehend. And all we've done is added a few oxygens. What's going on? Furthermore, look at the conjugate bases. Notice that the strongest acids, like perchloric acid, has the weakest conjugate base. pKb24 is extremely weak. It's much weaker than the other ones. Now if we think about it, this has to make sense. In order for an acid to be very strong, it has to want to give away protons. And that means its conjugate base has to be a very weak base. It does not want to take the protons back. You could not have a strong acid that also has a strong conjugate base. Can't be. All strong acids have to have very weak conjugate bases. So that's worth noting. But the next question will be, well, why? What makes adding oxygens affect the acidity so much? So the key to understanding what makes an oxyacid strong is to look at its conjugate base. So I've drawn the conjugate bases of these 4 oxyacids. And I've drawn all the possible resonance structures for these conjugate bases. So look at perchlorate. Recall that we can draw 4 different resonance structures in which the negative charge is spread over 4 different oxygen atoms. Now the negative charge is what makes perchlorate a base. A base is an electron donor. That's the definition of a Lewis base. If the negative charge is on one particular atom, it's going to be more able to donate because the negative charge is more concentrated. But when the negative charge is spread out over 4 different atoms, you can think of it that this negative charge is diluted. It's spread out, and so none of these oxygens is particularly basic. None of them is a good electron donor. And so perchlorate is a weak base because it has so many oxygens to share the negative charge. And because perchlorate is a very weak base, it makes sense that its conjugate acid would be a strong acid. Perchloric acid is readily able to give away a proton and wind up with a negative charge on it. So what? It's got 4 oxygens to spread out and stabilize that negative charge. In the case of chloric acid, we can draw 3 different resonance structures for the conjugate base chlorate. So this negative charge is spread over 3 different oxygens, which means it's still a pretty weak base. None of these 3 oxygens is particularly happy or pleased to give away the negative charge. It's being spread out on all 3 oxygens, and hence chlorate. It's not as weak a base as perchlorate. It's a stronger base than perchlorate, but it's still pretty weak as far as bases go. It's nowhere near like hydroxide, where just the oxygen has a pair of electrons to donate. And the conjugate base of chlorous acid is chlorite. We can draw 2 different resonance structures. So the negative charge is spread over 2 oxygens. It's spread out a bit. And so it's more basic than chlorate. That is, it's better able to donate a negative charge, but it's not as good as hypochlorite, in which only 1 oxygen has the negative charge. So of all these 4 bases, which one is most basic? Hypochlorite is most basic. Why? Because 1 atom holds all the negative charge, and that's going to be a more reactive atom, a better electron donor, a better Lewis base. Now you say, well, are there any other possible resonance structures we could draw here? What about the possibility of this? What if one of these non-bonded pairs of electrons came down here? What would that form? Let's try it out. It would form oxygen with a double bond and be neutral. What happens to the chlorine then? Well, how many electrons does chlorine own? 2, 4, 6, 7, 8. So chlorine is now -1. Yes, that is possibly another resonance structure. However, it is also true that whenever there's a negative charge present, it is most likely to be on the most electronegative atom, right? Oxygen has electronegativity of 3.5, chlorine's only 3, and so the negative charge is pretty much exclusively on the more electronegative atoms. So if this even exists, it would be a very small contributor. And so that's basically the reason. Let me recap. What makes an oxyacid strong is that it has many oxygens. Why does that make it strong? Because the conjugate base then, which has a negative charge, will have that negative charge spread over many of those oxygens. The fact that the charge is spread out, you can think of it as being dilute. Therefore, none of these oxygens is particularly negative. They're only 0.25 of a negative charge. They're very weak electron donors. When you have the negative charge concentrated on a single atom or fewer oxygens, then they become more basic. Hence, a strong oxyacid can only be strong if it has a very weak conjugate base. What makes it very weak is a lot of resonance structures where the negative charge can be spread out by resonance. It's a very useful concept, which we can understand by drawing these Lewis structures and resonance structures. I want to revisit the resonance structures of bicarbonate ion for just a minute to alert you to an error that I see students making from time to time. Hopefully you can avoid making this error. Sometimes I see students thinking they need to somehow include hydroxyl oxygens in sharing the negative charge in a resonance structure. So they'll draw something like this. What I'm drawing doesn't exactly make sense to me, but here's what I'm seeing. Sometimes they'll take a pair of electrons and bring it down towards this other oxygen, the hydroxyl oxygen. Well, that isn't correct for a couple of reasons. First of all, you can't move a pair of electrons beyond its own space. It has to stay attached to the same atom. That's the rules for resonance require that electron movements always involve just strictly the same atom. Right? So we can't go from one oxygen to another oxygen. The pair of electrons has to stay attached to the original oxygen. Secondly, if this actually occurred, what would you get? Well, let's take out this pair of electrons. It's going to be no longer negative, and it'll actually become then positive. Let me put it in red because it's wrong. And that would give us a double bond down here. And that means that carbon becomes negative because carbon has 5 electrons that it owns, and it's got 10 in the valence shell. And you see all the problems with this. This is wrong for a number of reasons, right? Carbon is not an anion. Carbon can't have 5 bonds on it. So the point to get here is that hydroxyl oxygens are not involved in sharing electrons in resonance structures. So what does share them? Well, the doubly bonded oxygens share the negative charge along with the negatively charged singly bonded oxygens. Those are the only oxygens that you share electrons between in resonance structures, not the hydroxyl oxygens. So that's an error you want to avoid making. Just be careful. So that's probably enough for this lesson.